that? Oh, okay, for the license. Yeah.
That's moving forward now. So that makes me think we can get it on here. No, we got that. Wait on me. $5 for this? Still lining on the end. It's all right. So we'll just give us more options.
They told him, I was like, yeah, some.
It's already still.
So it just makes more sense.
I should have placed down.
I twisted it.
Focused
on the mom.
You're gonna kill it at Lowe's. You're the smartest. Wait, wait. Nicholas, you should look at what Nick and Trump's names are on there.
You should look at some red.
That means that it's the other one.
Paradise? No, it relaxes me. It takes some stress off.
Ready to be live.
Okay, so, quick reminder of the schedule. So, regular class today, starting today, we cover will not be on the test for Wednesday next week. Let's see, we'll do matter days today. Turning homework will be the quiz at the end of class. There is a practice exam that is up online, so you can go and try that out. I got asked what chapters will be on the exam. It'll pretty much be chapters 22 through 26, so everything in circuits and magnetism is fair game for the exam. Any questions before we start?
Will we have homework due next week?
You will not have homework due next week. I don't think you will have homework due next week. I'm pretty sure, yeah, no, you're not going to have homework due next week because the test is on Wednesday and then we're not going to have covered enough stuff.
Okay.
Test is on Wednesday. Any other questions? Today's going to be a weird class. So let me start by kind of reviewing some stuff from last semester that will hopefully help you out with this. Today's going to be weird because we're getting into the part of the course that's is very difficult to explain because nobody really understands it. This is the modern physics part of the course. I'm not going to be able to explain it well because I don't understand it. The reason I don't understand it is because my professors didn't understand it. And the reason they didn't understand it is because nobody understands it. And this is the way I like to put it is, normally, if I do my job correctly, for the most part, you should come away from class feeling like you learned something. And hopefully, I made things make a little bit more sense. Today, if I do my job correctly, you should come away feeling very, very confused.
So every day.
Whether or not I do my job successfully is another thing. But today, you should come away feeling very confused because this is very confusing stuff. The good part about it is that mathematically, we're going to violate your intuition today a little bit, I think. But I want to remind you a couple of things from what we did on waves. So let's say I had two waves coming in. We'll call this wave 1 and wave 2, and I look where they are at different spots. Well, here, if I look at what this wave is doing, both of these waves are going up at this point. So if those two waves combined at that point, I would get the sum of those two waves, so that it would go up even more. Last semester, we called that constructive interference. The two waves could add up these spots where they were both going up. But we also had this other case, where again, let's say I have a wave that looks like this, and then another wave that looks like this. And if I look at these two waves adding up, well now, when this wave is going up, this wave is going down. So if I put those two waves on top of each other, if they interfere with each other, when one's going up, the other one's going down, what do we call that? Constructive interference. So that's going to play an important part in what we're going to describe today. Because we're going to be talking about matter waves. Now, how many of you guys have heard of matter waves or wave-particle duality in your chemistry or other classes? A couple of you guys. So, the difficult thing about this is that there's not really a good model in your everyday experience that I can compare what electrons and all other particles in the universe really act like. So let me start off by saying what they don't do. If I look at an electron in an atom, well, when you hear the word matter wave, you might think, well, maybe the electron is kind of going up and down like this. It's kind of jiggling around as it's going forward. That is not what it means. I also can't describe electrons as being like little planets going around the nucleus, where the nucleus would be the sun. It's not like a little solar system. I also can't say the electron is attached to the atom by a spring. That doesn't work. I can't say the electron is some cloud around the atom. None of these, all of these are just fundamentally not the right picture. They're not bad as a very coarse picture, but they don't really describe the way electrons actually act. The way they do act is, in my opinion, I think, is probably the deepest question in all of physics. And I would even venture to say the deepest question in all of science, because it gets to fundamentally, it really is a fundamental question of what does it mean to measure something? What does it mean to take data on something? The other thing I'll say about this is that, again, if I do my job correctly, it's going to seem like I'm telling you some sort of paradox. But if you look at it logically, there's nothing paradoxical about how I'm going to describe this. It should violate your intuition, but there's not going to be any logical paradoxes. I'm not going to say something that fundamentally contradicts the rules of logic. But I do want to do, to do this, to really explain it, I think it's best to do a thought experiment. And Einstein was kind of famous for doing thought experiments. He had a nice word for it. Of course, he spoke German, so the German word is called the Gedanken. We're going to do a Gedanken today. Not just use a thought experiment. We're going to do a few thought experiments. We're going to do, first we're going to do a thought experiment with bullets. Then we're going to do a thought experiment with waves. And then we're going to do a thought experiment with electrons. Pick your favorite part. It'll work for all of them. Okay, so let's start off with our thought experiment with bullets. We are going to suppose, this is called the two-slit experiment. It's one of the famous experiments in physics. We're going to suppose that I have some source of bullets over. In this case, it's a gun shooting off bullets in all directions. It's a very wobbly gun. It doesn't just fire straight. It kind of shoots things off randomly in a bunch of directions. And I am firing that at a wall with two holes in it. With two slits. So the bullets are going to come off in all directions. And some of them are going to go through the first hole, some of them are going to go through the second hole. So since I'm going to be talking about these holes a lot, I'm going to call this hole number 1, and I'm going to call this bottom hole number 2. And what we're going to do is we're going to measure where those bullets end up. So I'm going to put another wall behind the first wall. Put another wall right here. And on that wall, I'm going to put a detector. And the detector's only job is really just to count where the bullets go. And we're going to, so what I can do is I'm going to move my detector up and down. I'm just going to, the detector's basically just going to catch the bullets. And I'm going to count how many bullets do I get in an hour. So let's do this a couple of different ways. To start off, I'm going to actually block off hole number 2 so that the bullets can't get through. We're just going to look at what happens in hole number 1. We're going to detector up and down. So from hole number 1, what you'll find is that the bullets are going to come through, and they'll bounce through like this. And I should get a bunch of different bullets around directly across from hole number 1. So maybe I get a few bullets here, and then maybe every once in a while one ricochets off to the side. I start counting this up. And if I count this up over a long period of time, and I make a histogram of where my bullets showed up, what we'll find is that I get a plot that looks kind of like this. These are the bullets that come through hole number 1. Any questions so far? Pretty straightforward so far. All right, I can also do the same thing with hole number 2. So now I'm going to open hole number 2. Close off hole number 1. And hole number 2, well, very similarly, it's going to get a lot of bullets coming through. Maybe every once in a while you get some off to the side because of the ricochet, different directions. And if I plot, I make a plot of the number of bullets I get at different locations. On hole number 2, I get a plot that looks like that. These are the bullets that went through hole number 2. Now let's say I open both. I'm going to leave these two plots up here. And I'm going to say, let's say I measure what happens if both holes are open. Both holes. Well, if the number I get through hole number 1, if I call that N1, and call the number I get through hole 2 N2, it makes perfect sense that if I open both holes, then I'm just going to get N1 plus N2. The number of bullets I get is, it makes perfect logical sense to just say that the number of bullets I get when both holes are open are the same that I would have gotten through hole number 1, plus the same I would have gotten through hole number 2. You usually get a lot in the middle. There might be a dip in the middle if the holes are really far apart, but if the holes are pretty close, there's a good chance I won't even see the dip. But I'm going to get some big distribution of bullets that looks like that. This is the number of bullets through holes 1 and 2. Now, there's two very important parts of this that I want to emphasize. I'll get out of here. In the case of bullets, you always only get one bullet. Let's say that these are very, very strong bullets. They never break in half and then split in two. You always get one bullet at a time. Always find one bullet at a time. The second part of this is that I just get, if I look at the number of bullets from both holes, I'll say the total number, I'm just going to get N1 plus N2. I look at any spot, and I count up the number of bullets I got at that spot from hole number 1, and I add that to the number of bullets I got from hole number 2. I always just get the total number of bullets when both holes are open. That's bullets. That's a pretty straightforward case. Any questions on that? Okay. Well, now I want to do the case. I want to do a case with water waves. So let's say I set up a very similar experiment. All right. Set up a very similar experiment. But now, rather than sending bullets through the two holes, I'm going to send water waves through the two holes. We're going to do pretty much the same experiment. So again, I've got a wall with two holes in it. Except this time I'm going to put my wall in a tank of water. So I'm looking down on top of the tank of water. So let's say we're looking down at the pool. And let's say I just start dipping my finger in the water. When I do that, we should start to produce waves coming out. As soon as I dip my finger in the water here, we're going to start having water waves coming out, spreading in all directions. Again, we're just doing the same experiment, and now we're doing it with water waves. Now, water waves are, of course, very different from so if I look at what goes on with water waves, the water wave is not like a bullet in that, a bullet is either in a spot or it's not in a spot. Water waves are a little different. Water waves, I don't really get a bullet in a spot or not in a spot. I get some amplitude of water wave because the water is sloshing up and down. So instead, we're going to measure the sloshing up and down, which means we're going to be measuring the amplitude of the wave. No longer restricted to either having the bullet or not having the bullet. Now, the amplitude can take different heights in different locations. So I send these water waves through my slit. Again, I have my two holes, hole number 1, hole number 2. And again, what I'm going to do is I'm going to block hole number 2. And I'm going to look at what happens. I'm going to look on my back wall over here and see where is the water sloshing up and down the most. Is the water bouncing up and down on the side of my water? And again, what you'll find is right across from the hole. The wave's going to come through. It's going to spread out into space. Talked about that last semester. And what you'll find is that the water coming through hole number 1 sloshes up and down the most right in front of the hole. So I can call this the amplitude of the wave through hole 1. The wave comes through the hole, hits the back wall, and starts sloshing up and down on the wall. The wave's going to be, you're going to see more sloshing right near the hole than you are as you get further away from the hole. Do the same thing for hole number 2. Block off hole number 1, I look at hole number 2. Again, I will get a wave that looks like this, except now this is the amplitude of the wave as it passes through hole number 2. That one gets a little bit interesting because we know that when I open both holes, the wave coming from hole number 1 is going to look like this. Maybe the wave coming from hole number 2 looks like that. And there are going to be spots on the back wall where the waves are going to cancel each other out because they have that destructive interference. So if I look at the amplitude for both holes, what you're going to find is that we're adding those two amplitudes together. But the total amplitude I'm going to get is going to be something that looks like this. Places where the waves are canceling each other out, you get destructive interference. You get places where the waves are adding up, you get constructive interference. And if I want to look at the intensity of the wave, it's not the same as just adding the two amplitudes together. Wave intensity actually goes, so wave intensity, I'm just meaning the energy of the wave. Where is it sloshing up and down the most? the wave intensity, I get, actually by adding the two amplitudes together, if I call this amplitude A1 and I call this amplitude A2, I add the two of them together, but then I square it to get the intensity. I'm adding the squares of them. And sometimes they're negative, sometimes they're going to cancel out.
Is that absolute value of this?
Yes.
Okay.
Actually, amplitude's a bad word here. Really should say, I'm going to say the height of the wave. I'll still call it A, so I'm going to say the height of the wave. Because the amplitude in principle is always positive, but the height of the wave could be positive. But it's just the same wave phenomena we talked about last semester, where you have constructive and destructive interference depending on how far each of the two waves has traveled. So that's waves. It's a little bit more complicated, but still fairly straightforward. Any questions on the wave stuff, constructive and destructive interference? Okay, well now let's do, we make point two. Point two is that rather than just adding the total, just getting the number of bullets plus the through hole 1 plus the number of bullets through hole 2, when I add the amplitudes together, I do this, and we get some interference. And the waves cancel out. Now we want to do exactly the same thing with electrons. And the first thing we want to say is that electrons are like bullets. They're like bullets in the sense that you always only get one electron. You never get half an electron like I could with an amplitude. So much like bullets, you always find only one electron at a time. So let's say we have an electron gun over here, or not electron gun, you can think of that as just being like a cathode ray tube, kind of like the thing that produced the green line that we showed you earlier. Again, I'm going to measure which holes the electrons come through. So we start off. Like before, I'm going to block off hole number 2, leave hole number 1 open. Just like before, bullets, I'm going to get a lot of bullets, well, a lot of electrons near the hole, and then the further out I get, I might get a few. But I'm going to get a curve that looks like this. If I add up all of the electrons and make a histogram, the histogram is going to have lots of electrons coming straight through the hole, and then smaller and smaller amounts of electrons going off to the side. Electrons again, we can do the same thing for hole number 2. Block off hole number 1 now, open hole number 2. Again, you get lots of electrons in the middle. And then fewer and fewer electrons the further away from the hole. So now, both holes. Again, let's see. So if an electron goes through this hole, it ends up probably over here. If an electron goes through this hole, it ends up probably over here. I add the two of those together, I get something that looks like this. Lots of electrons in the middle, no electrons over here. Lots of electrons at this peak, no electrons over here.
Why would we use that?
If I knew that, I would be a rich man.
So that's just how it's.
That's how it is. That is when you shine an electron through two holes, you get this pattern. That should bother you. It looks like it bothers you. You look like you're ask me a question. That's the best way to do this at this point.
Still formula.
Somebody else ask me a question. Yeah.
How do they interact when you're only firing one at a time?
How do they interact with your
There has to be some interaction between the electrons if they're being deflected into those set bins, I guess, if you will.
the holes?
Yeah, the whole. On the right side when you're getting the output, you're only firing one electron at a time.
Correct.
How are they interacting with each other? Because there has to be some sort of interaction if they're going to those specific places.
They do not necessarily have to, they don't have to interact to get this down. So I can do this with only one, even if I had one electron. Forget electron now. Say I had one electron. And I took my one electron, like a baseball, and I threw it. And then I went over here and said, all right, where did you go? And I come back with my same electron, throw it through again. Do that a bunch of times. With both holes open.
And how do they know that both holes are open? Seriously.
That's tricky. I don't know.
I mean, don't they have to physically close the holes?
Yeah, you bring up a good point. So, let's suppose for the moment, let's take, I'll take this as a proposition. Let's take as a proposition, I fire an electron, and it happens to go through hole number one. Well, hold that thought. Let's take as a proposition that I know the electron goes through hole number one. All right, well, what should happen should not be dependent on anything that's going on through hole number two. All right, if it goes through hole number one, whether this is open or closed, that shouldn't matter. And yet it does, because here, I get lots of electrons right in front of a hole. But as soon as I forget doing anything to hole number one, all I do is open hole number two, and all of a sudden electrons stop going there. Yeah.
It's like a puddle of marbles.
Is it like a puddle of marbles?
Okay, because like marbles can bounce off of each other. And so like you just let them in. It's kind of like water.
So it could be, so you might think that electrons, maybe because I'm firing off a bunch of electrons, the electrons are bouncing off of each other. So that when I have the two holes open, when they bounce off of each other, they combine to make that weird screwy pattern. The problem is that I can fire one electron, per day, and I'll still get that same pattern. Yeah.
Is it kind of like if sound? Okay, so is it kind of like, how like jets, like they create a sound?
Okay.
Is it kind of like that, like the electron is a jet, and then everything else, and it kind of creates like its own sonic boom?
I'm not sure I'm getting the analogy.
I think he's saying that it leaves kind of a path, like a trace that the others are influenced by. But if you fire one a day or one a week, you can still get that. Then.
Yeah, so I would say it's probably not like that, because again, I can do this with just one electron.
But okay, so like you fire your bullet, And so then it's traveling at the green line. And with every like movement forward, is it kind of like creating like a circle around it?
Well, people have tried to come up with lots of different explanations like that. So try to find some explanation, some analogy that we can compare this to that would explain why we get this. And at least so far, all of them have failed. No one has been able to come up with a mechanistic way of figuring out why electrons do this. By the way, it's not just electrons, all particles do this.
It's matter.
It's matter does this. If you take a molecule, a buckyball, they actually did a buckyball experiment, so you get that same matter.
So you think it's kind of like if, so you think it's kind of like the electron is like being shot and then it's like moving every single particle out of the way and they start to bounce off each other, and that's why you get this kind of shape like this?
I would say it's not necessarily, I mean, if they were just, it's not just a matter of it repelling because it's an electron or negative things or other negative things. This works even if I do it with a neutrally charged particle.
Well, I'm talking about going back to kind of the matter thing.
Yeah.
So like literally like the matter is just kind of like bouncing off each other. So like photon's kind of like a bullet and then it's just moving
It
everything
depends on
apart.
what they're doing that in vacuum, because if they're doing that in vacuum,
They're doing it in vacuum.
yes, there's no work, there's no.
But even in like a vacuum, there is some kind of, isn't there?
Well, there's space, but what do you bounce off of? It's just empty space. What we can say, even though this is screwy, and it gets a little bit screwy, what we can say is that even though electrons always come in lumps, so they're like bullets, that they always come in these one at a time, one big lump at a time. We know they get distributed like a wave. So we can say that the probability of the electron being in place is proportional to, I don't even know what these are. So if we don't know what they are, we just call them the probability amplitude. This is also known as the wave function. That you've seen if you've ever plotted atomic orbitals. Atomic orbital is the wave function. What's that?
Size.
Yeah. Yeah, these are the Greek letters psi. There was a question in the back before.
I was wondering what happens if you, well, when you track which slit the particle goes through.
Ah, that's a good question. So you could say, all right, I know if the particle goes through hole number 1, it's going to be close to hole number 1.
Yeah.
This tells me it's not going to be close to hole number 1. Let's see which hole it goes through. Let's just watch which hole it goes through, right? Because I know if it goes through hole number 1, I've got to get particles up near hole number 1. That's the only thing that makes logical sense. Let's try that. How can that be? I told you it looks like this. So let's try this experiment. Let's say we put a light bulb right here. And the light bulb is sending off light in all directions, and whenever the charge goes through one hole, it will emit like a little flash of light. So we can watch them. We can set half the class up in front of this hole, half the class up in front of the other hole, and then some of you guys will be like, all right, I'll be like, all right, I just detected one, and people over here will be like, all right, I saw it go through hole number 1. And then the other group will be like, oh, I saw the next one go through hole number 2. You can just count which holes they go through. So we can do that. Actually, let me leave this here. Just yet. So we get 2 columns. So, all right, I know this one went through hole number 1, I know this one went through hole number 2. And we compare again. So we measure, right? Went through hole number 1. Let's look at what happens to the distribution when we know they go through hole number 1. All right, you guys count it up. Again, you get this distribution.
But it still goes.
Well, if I just forget the group, let's say this half of the room does hole number 2, this half does hole number 1. All the people who are measuring where the particles went when they go through hole number 1, they get a curve that looks like this. The other half of the room, they measure what goes through hole number 2, it looks like this. So it's got to be true that if I add these two together, I've got to get something that looks like this. But I just told you it looks like this. Now, when you do it this way, it looks like this. Let's think about this. As soon as I put the light there, as soon as I know it went through hole number 1, I get the sum of the two curves and it looks like this. It looks like one big curve without any interference. Or to put that another way, as soon as I measure which hole the particle went through, I screw up the experiment. The very act of looking at what the particle is doing affects how the results come out. So I can't get this curve as soon as I know which hole the particle goes through. Let me give you the physics interpretation of this. Physics interpretation of this is that the particle is actually not like a little ball, it's not like a particle on a spring, it's something completely different, something that you don't have any experience with in everyday life. What it is it comes out like a wave. It starts to act like a wave. But as soon as you look at it, as soon as you try to take any possible conceivable measurement of it, that collapses it back into a particle. That's what the data would suggest.
So is this like
This is quantum mechanics. There are two kind of major pillars of modern physics. One of which is special relativity, or well, relativity in general, not just special relativity. Relativity deals with time slowing down and E equals mc squared and a bunch of other stuff. Relativity is weird, but once you study it for a while, it makes sense. This is quantum mechanics. Quantum mechanics is weird, and once you've spent your entire career studying it, it still is math. There's never a good feeling about this. The weird thing is we lose the ability to say the particle went through one hole or the other. Because I mean, your temptation is to say, all right, well, the particle's really, it really is kind of like a little ball. An electron really is like a little ball, but it's just doing something screwy, which is why I get this pattern. But I know if it goes through hole number 1, then I'm going to get particles here. And I don't get particles if hole number 2 is open. So I can't say it went through hole number 1 or hole number 2. I have to say, well, maybe it went through both holes, but you can't say it definitely went through hole number 1 or definitely went through hole number 2. Yeah.
What if you were to like directly point your electron gun so that it only pointed through hole 1, but left hole 2 open? Would you get the same result?
Do you mean if I put my gun right here?
If you well, yeah.
If there's not a path, I mean, for the electrons to go through hole number 2, then you're just going to get the distribution. Because basically, as soon as I put my gun through here, I know the electrons are going through hole number 1. So then they flip like arrows. That's the first.
So you said that this thought experiment is being done in like a vacuum.
Yeah. By the way, you can actually do this. This is not just a thought experiment. This
Let's do it.
was an actual experiment.
Okay, so it's done in a vacuum. I thought that only light moved in a vacuum. Or I thought that energy could only move.
Well, all right. So technically, it's not a vacuum because there's the electron moving through it. But aside from the electron moving through it, it's a vacuum.
So can electrons move in like the vacuum space?
Yes. So right now, off in the vacuum of space, the sun is emitting lots of light at us, but it's also emitting protons and electrons and other things. It's just like throwing a ball in a vacuum, which you can do. We got a big vacuum chamber. We have Professor Ditzler come and set up a big vacuum chamber for us. You can throw a ball in it. the ball would actually move much better in vacuum because there's no air resistance. As I started this off, I told you this should leave you with an uncomfortable feeling. The universe is a weirdly screwy place. However, it's only uncomfortable because human beings tend to be kind of vain. Right? I mean, we think like our everyday experience is the way the universe should work everywhere. But there's nothing that says that the universe, on a very tiny level, when you get down to fundamental particles, has to work the same way that we're experienced with when we're working with on a big scale where baseball has 10 to the 23rd particles in it. Human beings, there's nothing that says that the universe has to be that way. And it turns out it's very different than we would have expected it to be otherwise. One of the reading questions I got was, does the matter wave stuff explain how teleportation works? And it does actually. So at the beginning of last semester, we talked about in the first day, I put up a bunch of slides of different physics things that we know existed, and teleportation was one of them. Yeah. On a very tiny scale. You can teleport things like photons, and I think the largest thing that's been teleported was like 8 atoms big. But it does happen. It's not even that new actually. It was done like 15 years ago.
What?
You mean I know who you're talking. It's not Manchu. It's I know who you're talking.
See, I've never been able to actually say
It's the guy on the History Channel, the old Asian man with the kind of awesome white hair.
Yes.
Yeah, I know who you're talking about. I forget his name. It's not Manchu.
It's the wrong
Well,
Machu Picchu, I think, is a mountain. More questions about this? Now, the frustrating thing about this is it violates your intuition and it's very screwy, and you really want to say, there's this temptation to be like, well, how can it be this way? It is this way. We don't know. It's okay to not know why things are the way they are. Just because they violate intuition doesn't mean they violate any rules of logic. The good part about this is that the mathematics behind this is fairly simple. At least the stuff we're going to do is fairly simple. So in some sense, if you get over the hurdle of this, of trying to understand how this could be conceptual, the mathematics part of this, the modern physics stuff, is not too hard. So the stuff we're going to do in class, the problems, are going to be very similar to what you've seen in chemistry class before. They won't be so difficult. I mean, they'll still be difficult, but I would argue that they're not as difficult as the circuits or the magnetic field stuff that we covered earlier this semester. That's what I wanted to say. We'll come back. More questions about this. It should bother you, but that's okay. The universe is fun.
So this is where Einstein was.
No, Einstein.
Played dice. That wasn't play dice.
Yeah, Einstein had this. Einstein had this famous quote about God not playing dice, and Niels Bohr wrote something back to the effect of, "Oh, yeah, but it's not really our position to tell God how to run the universe." Speaking metaphorically, Einstein had a really good year in 1905 when he came up with relativity. After that, he spent 11 years kind of developing the math to come up with a more general theory of relativity, and after that, he spent the rest of his life complaining about quantum mechanics. Because Einstein made a lot of statements about the universe not being able to, not being random numbers. But every experiment that Einstein tried to come up with to show that it wasn't random ended up working in the other direction.
So is it completely random, or is that the configuration you're gonna get? every
Well,
time?
this is the configuration that you're going to get, but I cannot predict which of these homes an electron, a single electron, is going to come out. I know that if I get a bunch of them, they'll make this shape. But it is random which, for single electrons, it's random which place it's going to end up.
But I thought that you said that if you only shoot one electron per day,
Yep.
that's the thing you get.
I will get this shape, but let's say I shoot an electron right now.
It's
Is it going to end up here, or is it going to end up in this, or this? That I don't know. That there is no way to predict. Which is related to something called the uncertainty principle, which we'll talk about. All right, I want to pass out the quiz to make sure you guys have time for that. I think it's all